reflection. Actually, a reflection. What is the meaning of this reflection is, suppose a transmission line is given, terminated with some load, ZR, having some characteristic impedance, Z0. This is a sending end, and sending end I am transmitting some energy. So the energy is propagated, it reaches the load end. So load will absorb some energy and it will dissipate some energy. And some energy will reflect back. Why this reflection occurs is because of impedance mismatch. Impedance mismatch. That is, here the load is terminated with ZR. The characteristic impedance of the line is Z0. That load is terminated with some load ZR value. So what happens? Obviously there is some reflection back from the load end to the sending end. Generally this reflection occurs when there is an impedance irregularity, that is, termination impedance is not equal to characteristic impedance of the line. This is indicated by, this reflection is indicated by a parameter known as reflection coefficient. Reflection coefficient. So we can indicate with the symbol K, tau, or some rho. There are many symbols, you can use whatever it may be. So K, tau or rho. That is, suppose if VI is the incident voltage, suppose VI is the incident voltage and VR is the reflected voltage. Here is the reflected voltage. Then the reflection coefficient K is equal to, the reflection coefficient K is equal to reflected voltage by incident voltage. Reflected voltage by incident voltage, that is equal to VR by VI. This reflection coefficient also we can define for current also. That is, suppose if II is incident current, IR is reflected current, then the reflection coefficient K is equal to minus IR by II. This is the negative of reflected voltage by incident voltage, whereas for voltage it is positive voltage only, VR by VI. Why we are taking this current as a negative is because reflected voltage, if considered positive, will circulate an opposite current to the previous one, because I am considering the reflected voltage as a positive one. So if reflected voltage is positive, what happens? Suppose I am considering the incident voltage like this, VI. This is a reflected voltage I am considering positive, that is VR. So generally current will from positive to negative. So reflected voltage will generate a current like this, IR, whereas incident voltage will generate a current IA like this. That is, the reflected voltage generates a opposite current to the previous one. That's why I am considering the reflected coefficient for current definition is minus IR by II. Generally, this derivation for K is, I am directly giving a formula for reflection coefficient. K is ZR minus Z0 by ZR plus Z0. Very important formula to keep in mind. That is, the reflection coefficient of a transmission line is ZR minus Z0 by ZR plus Z0, where ZR is load impedance, Z0 is characteristic impedance. Suppose ZR is equal to 0. ZR is equal to 0. 0 means what? Short circuit line. Short circuit line. Then what is the reflection coefficient? Reflection coefficient is equal to 0 minus Z0 by 0 plus Z0, that is minus 1. Short circuit line. Suppose ZR is equal to Z0. ZR is equal to Z0 means what? Matched line. Matched line. Then what is K value? K is equal to 0 because Z0 minus Z0 by Z0 plus Z0. That is, Z0 minus Z0 is equal to 0. That is matched line. That is, if a line is terminated with its own characteristic impedance, then the reflection coefficient is equal to 0. Reflection coefficient is equal to 0 means what? VR by VA is equal to 0. That is, reflected voltage is equal to 0. That is, there is no reflection at all. All the energy what we are sending from the input side is observing at the output side. There is no reflection at all. That's why it is called maximum power transfer theorem. Maximum power transfer will take place whenever the load is terminated with its own characteristic impedance. Similarly, if ZR is equal to infinite, that is, ZR is equal to infinite means what? Open circuit line. Open circuit line, what happens? ZR is equal to infinity. Put ZR is equal to infinity. So therefore K is equal to, I am taking ZR common here, 1 minus Z0 by ZR divided by ZR common, 1 plus Z0 by ZR. Right? ZR cancels. Put ZR is equal to infinity. So this term cancels. The remaining thing is 1. The remaining thing is 1. Therefore, if ZR is equal to 0, ZR is equal to Z0, ZR is equal to infinite. K is equal to minus 1 here, K is equal to 0 here, K is equal to 1 here. Therefore, the range of values for reflection coefficient is, therefore, the range of values for K is equal to minus 1 less than or equal to K less than or equal to 1. That is, the reflection coefficient value lies between minus 1 to 1. Actually, the concept of this topic is, suppose I am considering, for example, open circuit line. Open circuit line means ZR is equal to infinite. What is K value? K value is equal to 1. VR by VA is equal to 1. VR is equal to VA. VR is equal to VA. That is, the entire voltage reflects back. The entire voltage reflects back. Also, the similar case for short circuit also. Even short circuit, what is the thing? VR by VA is equal to minus 1. There VR is equal to minus VA. Of course, there is a inversion in the magnitude. But the entire input voltage is reflected back. That is, If it is either short circuited or open circuit, what happens? The entire input is reflected back. Suppose for example here open circuit case, what happens is, this is open circuit line. I am transmitting some energy. Open circuit line means the current is 0. Generally what happens is, under open circuited condition, when the incident wave approaches the load end, the magnetic field collapses. The magnetic field collapses. What is the reason? Because the current is becoming 0 there. At the load end, current is 0. That's why what happens, when the input wave reaches the load end, magnetic field suddenly collapses. This collapsing magnetic field produces an electric field. This is a very beautiful concept of Maxwell's equation. We know it very well. Magnetic field will generate some electric field will generate some magnetic field. This collapsing magnetic field produces an electric field which is added to the existing electric field, because here open end electric field presents because there is some voltage presents. So this additionally created electric field is added to the already existing electric field, and voltage at the open circuit end is increased. This additional voltage gives rise to a wave which travels back to the sending end. It travels back to the sending end. Here what happens for a open circuit case? The collapsing magnetic field will generate an electric field which is equal in magnitude to the existing electric field. Okay. So at load end, what is the total voltage? Already incident thing Vi and reflected thing plus Vi. So at load end, that is at that particular point, the voltage is double of the incident voltage. That's why this is also called as voltage doubling action. It's also called as voltage doubling action. That is open circuit line is for a voltage doubling action. Similarly, for a short circuit, what happens? Electric field collapses because their current exists. Voltage is equal to 0. So as the input wave approaches the load end, what happens? There is a sudden collapse in the electric field. That sudden collapse in the electric field generates a magnetic field which is added to the already existing magnetic field. Here IR by IA is equal to that is equal to K is equal to minus IR by IA. For a short circuit, this is short circuit case, this is equal to minus 1. IR is equal to IA. If you calculate the current at load end of a short circuit, what is the thing? The incident one is IR, the incident one is IA, the reflected one is again IA. So II plus II, total II plus IA. So it becomes 2 II. This is double of the input current at load end only. So the entire wave is reflected back. So this is also called as current doubling action. So here the important points to keep in mind is, for a short circuit case or open circuit case, what happens? The entire wave is reflected back. If it is open circuit case, there is no magnetic field, that is magnetic field collapses. So this is a voltage doubling action. It will create a voltage doubling action. Whereas in short circuit case, there is no electric field at the load end. Therefore, it will arise as a current doubling action. Which is very, very interesting. Now we will discuss another interesting topic, that is standing wave, standing wave ratio. Standing wave ratio. Standing wave pattern also. It is also called as VSW or voltage standing wave ratio. Voltage standing wave ratio. Generally, this is when a transmission line is terminated with some irregularity load, that is ZR not equal to Z0, we know that there is a reflection. There is a reflection. Suppose if ZR is equal to open circuit or short circuit, the reflection is maximum. The reflection is maximum. So what happens? There is a incident wave as well as some wave is reflected back. That is, again the wave incident on the input side, what happens? Again this wave will reflect back, because at input side there is no, there is only source presence. So something is absorbed, something is reflected back. Again the thing is reflected back. Like this the procedure continues. So after some time what happens is, as time tends to infinity, this forms a standing wave pattern on the line. Standing wave pattern on the line. This forms a standing wave pattern on the line. That is the incident voltage and the reflected voltage. Again the incident voltage and the reflected voltage combinedly. If you calculate and on the entire length, there will be some particular voltage at a point at a particular time. Okay, it forms a standing wave pattern on the line. This is defined as standing wave ratio. Yes, this is defined by standing wave ratio. Yes, this is S is given by magnitude of maximum voltage on the line by minimum voltage on the line. Also it is equal to I maximum by I minimum. That is maximum current on the line by minimum current on the line. Suppose generally it is indicated with VSWR. Generally we will consider the formula Vmax by V minimum. Or in general it is standing wave ratio. Standing wave ratio. That is, the standing wave pattern is something like this. Something like this. Something like this. Something like this on the line. This standing wave pattern is given by S is equal to 1 plus mod K by 1 minus mod K, where K is reflection coefficient. This is very important formula. Standing wave ratio S is given by 1 plus mod K by 1 minus mod K. Now we will see. We know that we will consider one by one case. Suppose short circuit. The first one is short circuit case. Short circuit case means what? ZR is equal to 0. Then what is the value of reflection coefficient? K is equal to minus 1. Then what is the standing wave ratio? 1 plus minus mod of minus 1 divided by 1 of mod of minus 1. This is obviously infinite. Obviously the value is infinite. Similarly, suppose open circuit case. Open circuit case, ZR is equal to infinite. What is K value? K is equal to 1. For this case, what is standing wave? 1 plus mod 1 by 1 minus mod 1. This also gives us to infinite. Finally, matched load or matched line. Matched line. Matched line means ZR is equal to Z0. What is K value? K value is equal to 0. K value is equal to 0. Then what is S? S is equal to 1. S is equal to 1. So now what is the range of VSWR value or standing wave ratio value? 1 less than or equal to S less than or equal to infinite. This is the range of a standing wave ratio. That is, it exists from 1 to infinity. 1 is for matched load, infinity is for either open circuit case or short circuit case. Now we will see how the pattern looks like on the line. Suppose I am considering for a short circuit case, or you consider first of all for a open circuit case. Open circuit case means open circuit line is like this. That is, voltage is maximum at the load end. Always draw the graph from load end. Voltage is maximum. So at this load end, voltage doubling action takes place. So generally voltage is maximum. So I am drawing voltage is maximum from load at load end. Voltage is maximum. So it will be like this. It will be like this. This is a clear sinusoidal wave. Here the thing is voltage maximum. This is for open circuit case. Suppose short circuit I am writing. Suppose this is voltage wave. Suppose if I want to draw the current wave. If voltage maximum means current is minimum. So current is minimum. So like this. Wherever voltage is minimum, current will be maximum. So it will be entirely opposite to voltage wave. Entirely opposite to voltage wave. Okay. This is a voltage pattern. This is current pattern. So you can get a more clear pictures from the textbooks. Suppose short circuit case. Short circuit case. For short circuit case, what happens at load end? Voltage is minimum. Voltage is zero. Voltage is minimum. So it starts from minimum, and the voltage standing wave pattern will be something looks like this. This is from load end. This is always load end. Remember, this is load end. What is current? Current is voltage is minimum means current is maximum. So here is maximum. It will wherever voltage is maximum, current is zero. Like this, it will be. This is a current pattern. This is a current pattern. In general, for a general transmission line terminated with ZR, the pattern is like this. The pattern is like this. Something like, you cannot say whether it is maximum or minimum. Some value, it may be either maximum or minimum. Maybe either maximum or minimum. How we know that here it is maximum or minimum? This is from the concept of open circuit and short circuit only. Suppose if you observe the open circuit case, voltage is maximum. Voltage is maximum means what is the tau value? Reflection coefficient. Reflection coefficient is equal to 1. That is positive. Reflection coefficient is equal to 1. Whereas for short circuit case, what is the reflection coefficient? -1. That is the reflection coefficient is negative. So in general, we can say that if reflection coefficient K positive means at load end we will get Vmax. At load end we will get Vmax. If reflection coefficient is negative, at load end we will get minimum. At load end we will get minimum. So this concept we can use, which is very, very important for solving problems. It is very, very important for solving problems. The thing is, suppose that load end is maximum, so that the reflection coefficient is positive. Suppose that load end it is minimum, the voltage is minimum. The voltage is minimum means reflection coefficient is negative. We have to consider like that. So like this, the standard patterns looks like.